Could you ride an elevator to space? Imagine stepping into a cabin, pressing a button, and ascending thousands of miles, not on a rocket, but on a silent, steady journey directly into orbit. It sounds like science fiction, a dream from a bygone era of boundless optimism. But what if this dream isn't just fantasy? What if the very laws of physics, which seem to forbid such a structure, also offer a tantalizing path to its construction? The truth is far more complex and far more fascinating than you might ever expect. The concept is elegantly simple. A space elevator is a colossal tether, anchored to Earth near the equator, stretching upwards into the cosmos. At its far end, a massive counterweight keeps the entire structure taut, balancing the forces of gravity and orbital mechanics. This isn't a tower in the traditional sense. Instead, it's a ribbon, perhaps just a few feet wide, held rigid by the centrifugal force of its own rotation around the Earth. It would extend far beyond geostationary orbit, where satellites appear to hover motionless above a single point on the planet. Climbers powered by electricity or lasers from the ground would slowly ascend this ribbon. They would carry cargo, people, and supplies, bypassing the violent, expensive, and fuel-intensive launches of rockets. It promises a future where space travel is as mundane as a trip to the next city. But the simplicity of the idea hides an almost insurmountable engineering challenge. The forces at play are immense. The tether itself would need to withstand unimaginable tension, pulling against Earth's gravity and the outward tug of the counterweight. No known material today possesses the tensile strength required for such a structure. Steel would snap under its own weight long before reaching even a fraction of the necessary height. We need something lighter, yet exponentially stronger. Enter carbon nanotubes and graphene. These exotic materials, composed of single layers of carbon atoms, exhibit incredible strength-to-weight ratios. A ribbon made from these could theoretically bear the load, but we can only produce them in microscopic quantities, not miles-long strands. Then there's the orbital environment. The tether would pass through the Van Allen radiation belts, exposing it to damaging particles. It would be a target for micrometeoroids and space debris, each tiny impact potentially catastrophic. The counterweight itself presents a problem. It needs to be massive enough to keep the tether taut, perhaps a captured asteroid or a specially constructed space station, and the entire system would need to be precisely balanced, constantly adjusting to maintain its geostationary position. But once you build a tower to space, could it even survive the storms and micrometeoroids? The sheer scale of the structure makes it vulnerable. A single, well-placed piece of space junk could sever the lifeline, sending sections plummeting back to Earth. Imagine the weather. High-altitude winds, lightning strikes, even the subtle gravitational perturbations from the moon and sun would exert forces on the ribbon. Maintaining its integrity and stability would be a continuous, monumental task. Several nations and private companies have proposed designs, from Japanese concepts involving robotic climbers to Russian ideas for lunar-based elevators. Each proposal grapples with these fundamental challenges, pushing the boundaries of our current technological capabilities. If we could overcome these hurdles, the impact would be revolutionary. The cost of putting a kilogram into orbit, currently thousands of dollars, could drop to mere hundreds or even tens of dollars. This would democratize space. Suddenly, building vast solar power satellites to beam clean energy back to Earth becomes feasible. Mining asteroids for precious resources, establishing permanent lunar bases, or even launching missions to Mars would transform from monumental endeavors into routine operations. It would fundamentally change our relationship with space, transforming it from a distant, inaccessible frontier into an extension of our planet. The environmental benefits are also profound, eliminating the need for polluting rocket launches. The materials we dream of may exist, hidden within the quantum realm of carbon atoms, but we are still generations away from producing them at the scale and purity required. The engineering challenges, the sheer audacity of building such a structure, remain staggering. A space elevator is more than just a feat of engineering. It's a testament to human ambition. It represents a future where the impossible becomes merely difficult, where our reach truly extends beyond our grasp. It's a vision that demands not just ingenuity, but patience, perseverance, and a profound belief in what humanity can achieve. We might one day step into the stars, but first we need to withstand the storm of space itself.